All right, well, let's go ahead and work a quick example problem in our video. We are tackling 2D particle equilibrium. This is, in my opinion, one of the key things for all of statics. Figure this out now. Watch more videos. We have a bunch of example problems we can take a look at. Get through this. This will keep showing up in more and more material. We're kind of laying the groundwork for things that we use almost the entire course. So let's get this figured out. Watch more videos if you need to, but we'll get you there. So our example, we have pulley A, our circle right here, is supported by cable AB going straight up and down, cable AC, our horizontal cable, and then there's a cable that goes from E around the pulley at A over to D that's supporting this 120 kilogram mass. We're going to try to figure out our tension in each cable. So 3 cables in there. We should be able to get all of them. The very first thing I would do on this problem is we're given a mass for this, kilograms. We always want to work with forces in here. We want to convert that from a mass to a weight. So our very first step, we can say, 1, convert mass to a force. Again, for us, that's just going to be weight instead of mass. So to do that, we just need to multiply by gravity. So our mass, 120 kilograms, times gravity, 9.81, will get us that our weight of this box is 1,177 newtons, which will be our first piece we need in here. From here, that actually gives us enough that I can say, what's my tension in EAD? Let's call that tension in cable EAD. Anytime that we have like a weight or a box, something just hanging off of a cable, we should immediately be able to say that our tension in that cable is whatever the weight of the box is. So we can get the TEAD, our first answer is 1177. 1177 newtons. And that's one of our 3 answers in here. I wouldn't make you do this, but we could come in and draw a free body diagram of our box. We'd have the tension, our cable going straight up, the weight going straight down, summing forces in the Y, we get our tensions 1177. But it's always going to work out to just be the weight of the box is the tension in that cable. Once we have that piece done, we can come in and say, we're working towards equilibrium in here. So let's draw a free body diagram. If we are in equilibrium, we're applying equilibrium equations, we should always have a free body diagram that goes with that. So our second step we'll say is draw a free body diagram. Let's make a free body diagram, FBD, of where everything comes together. Everything comes together at our pulley here at A. FBD of A. Remember, if we aren't given dimensions on this pulley, we can assume it's infinitely small. So even though this cable is a little bit off to the right here, not connecting dead in the center, we'll assume everything's in the very center of this. So we can get our free body diagram set up from there. So we'll redraw our pulley, just our circle. Actually, let's circle around what we're drawing. So we're going to circle at A. Make a quick circle. Everything that our circle just cut through in here needs to show up as a force in our free body diagram. So I cut through 1, 2, 3, 4 different things. All 4 of those need to be unknowns or need to be forces in our free body diagram. Some of them will be unknown, 2 unknowns, 2 of them are going to be known, TEAD. Let's come and draw that. So we're going to replicate our pulley. That's point A right there. I know going straight up from point A, I have cable AB. So I'll put that in as an unknown in here. This is the tension in cable AB, TAB. I have going straight to the right, cable AC. So I'll show it going to the right. A TAC, just coming up with some name, kind of makes sense. Tension in cable AB, tension in cable AC. I also have leaving this a cable going straight down. Let's label that in there. That one went straight down, and we know that's cable EAD. I already found the force in that one is 1177. So let's label it as a known. TEAD equals 1177 newtons. And then one last cable to get in here. I have EAD shows up again going down into the left. So it should be one force in tension, acting away from our point. So we'll show this going down and to the left. It's the same cable. This is still TEAD, so it's still known for us. TEAD here. TEAD. And it's still going to be 1177. 1177 newtons. Even though our cable has gone up and around our pulley in there, the tension in the cable never changes for us. It's always going to be the exact same as we move our way through things. So we know that one. TEAD. Let's redraw how that's labeled in here to get it all on the screen. This is TEAD. TEAD is 1177 newtons. From here I can come in then and just apply equilibrium. I have my free body diagram drawn. Now let's move to our equilibrium equations. So our third step is apply equilibrium. Apply equilibrium. And we're going to solve everything out. And solve. I have two equilibrium equations for 2D particle equilibrium, which means I can find two unknowns, which conveniently that would be TAB and TAC. If I'm tackling a problem like this, I'm going to look at that and go, is there one equation that I should start with? If I can do one equation and find one unknown, I should start there. It's going to make all of my math a little bit easier as I go through. I'm going to avoid a system of equations if I can. It'll help me be more successful. Being more successful means I make fewer mistakes. That's just good practice. For this problem, it doesn't matter. I can do some of the forces in the y and TAB is my only unknown. I can some forces in the x and TAC is my only unknown. So we just want to pick one of them. Let's sum our forces in the y direction. If I do that, positive for us will always be, unless we clearly define something different, but positive will go straight up in the y, so straight down will be a negative y force. Positive x goes to the right, negative x goes to the left. So summing forces in the y, we'll just work clockwise around this. I have TAB, it's entirely pointing up, so it's entirely in the y. I can just put the whole thing in here, TAB. I don't need to include an angle or any type of a trig identity in that because it's fully in the y. TAC is only in the x, that's no y component, so we'll leave it off. TEAD right here goes straight down, so subtract that off. Down is in the negative y, so minus 1177. And then we have TEAD shows up a second time. It's down to the left, so some of that goes in the x direction, that's the left part, but it does have a y component going down. So we'll have to include that in here as well. So minus, there's one thing we should have included in our free body diagram, is our angle on this. It's at a 3, 4, 5 triangle. Let's come back and add that in really quick. 3 was our vertical, 4 was the horizontal, 5 is the hypotenuse. With that in there, we now actually have our whole free body diagram. Get the geometry labeled. But we can solve this out. So if we have that triangle piece, we aren't directly given the angle. We have enough that we can get our trig identity solved out in here. So if I have our triangle and I'm looking for the y component, I'm just going to take the y leg divided by the hypotenuse times my total force. So 3 minus 3 divided by the hypotenuse, 5, times our total force, 1177. Really, this is telling us what's our ratio of height to base to hypotenuse for that force in here. If we know that ratio, we can get our sine would be opposite 3 divided by hypotenuse, 5. This is the sine of whatever angle it's going at. We can just shortcut a little bit. The y leg divided by the hypotenuse gets us the y component. But that's everything in the y. We're back to TAB going up here. We can set this whole equation equal to 0 and solve for TAB. We should just get from that TAB is equal to 1884 newtons, 1,884 newtons. Which if we had to use that in a new equation, we don't for this problem. But if we did, we can now put it in as a known value rather than a variable moving forward. We have one last equation to do. I can sum forces in the x. Summing my forces in the x direction, We're going to work our way clockwise around this again. TAB is entirely in the y, so we'll leave it off. TAC points to the right, straight to the right, it's entirely in the x, so we'll just put in TAC. No trig identity needed. This TAD goes straight down, even though it's negative in the y, it's only acting in a y direction, so I can leave it off. The only other thing I need in here is this x component of TEAD, the one that goes down and to the left. Because it points to the left, that's negative, so minus TEAD's x component. Which again, with those triangle pieces, if I'm looking for the x, I'll take the x leg divided by the hypotenuse. So 4/5 minus 4/5 times 1177 should get us to 0. Which I can solve that one. My last unknown is going to work out to be that TAC is equal to 942 newtons, which would be my final answer for our problem. Again, make sure we can get through particle equilibrium in here. This is going to keep showing up over and over. Free body diagrams are critically important for us. Equilibrium equations are at a key level. All that statics is. Make sure we can get through these. Watch more videos. We can get you there. But if this was helpful for you, don't forget to help me out and hit that like and subscribe button. We'll see you in another video.